Okay, so we have our final panel. And as the panelists are getting seated, I just want to give a plug for lunch. Please stay. I know it's been a long morning, but we do have boxed lunches for everybody if you're hungry. Okay, so thank you, everybody. My name is Tracie Owens. I'm a group lead in the Materials Engineering Division at the Lawrence Livermore National Lab. And our last panel, we're going to cover the L&L capabilities in climate tech. So we want to talk about some of the research that's been going on there, as well as the types of activities and skill sets that researchers involved in this area typically have. So to have this conversation, we have three leaders from the Lawrence Livermore National Lab who have joined us. We have Brandon Wood here, who is a deputy group leader and a center director. We have Sarah Baker, who is a group leader in energy and climate security. And we have Eric Duoss, who is the director for the Center for Engineered Materials. And so we want to start off the panel with them introducing themselves, talking a little bit about their work, their experiences at L&L, particularly in the climate tech space. And then I will pose a few questions to them, and hopefully that will get the audience thinking, and then we'll go to questions from the audience. Does that sound good? All right. So thank you. So I think I'm going to turn over to Brandon to introduce himself first.
All right. Thank you, and it's a pleasure to be here. So I'm Brandon Wood. I have a few roles at the lab. Actually group leader rather than a deputy, but my two main roles are one as the director of a center called LEAF, which I'll talk a little bit more about. And then I also am associate program lead for hydrogen at the lab. So I do a lot of work in the hydrogen area. I've been at the lab for about 16 years now. My background technically is in computing. So I'm very interested in how modeling and simulation plays a role in this sort of climate transition that we're entering now. A little bit about our center, which I think will sort of frame some of the technologies that we're interested in. So we have, the center is called LEAF, Laboratory for Energy Applications for the Future. And it's really focused on materials for energy applications. We have 4 focus areas. These focus areas rotate, but currently there are 4. One is energy storage, mostly electrical energy storage. So that's where our battery innovation sits. A lot of that work is in solid state batteries. We also do a lot of work in sort of testing and degradation of battery materials. Second area is hydrogen. This is the area that I'm personally working in the most. So in the hydrogen space, we look at hydrogen production technologies, mostly with renewable energy, but not exclusively. Both low temperature and high temperature processes for hydrogen production. We also do a lot of work in hydrogen storage, both underground geologic hydrogen storage and materials for materials-based hydrogen storage. So for sort of compact low pressure hydrogen storage. Our third area is carbon management. So that's an area that intersects with the other 2 guests on the stage and that you've heard a lot about already. In that space, on the materials side, it's really focused on both electroconversion processes, so a lot of work in catalysis and reactors for conversion of CO2 to commodity chemicals, for instance. And then also in the direct air capture space and in what's called reactive capture, so the idea that you can both capture the CO2 and convert it into something useful at the same time. Our fourth area is cross-cutting. We call it degradation and sustainability. Part of our core mission at Lawrence Livermore involves understanding materials failure. This is a personal interest of mine, and I think something that really bridges fundamental basic R&D and applied deployment. So trying to predict, understand, and ultimately mitigate how materials fail in the context in which they're expected to be utilized. The other piece of that, the sustainability piece, is really looking at things like critical materials and supply chain issues. We are a national security laboratory, so when we look at energy, we're also always looking through the lens of national security, and one of those challenges involves, how do we supply things domestically? How do we look for alternatives to materials that are difficult to source in the United States? So I think I'll pause there.
Excellent. Thank you, Brandon. That was a great introduction. Sarah, did you want to introduce yourself?
Sure. Hello, everybody. Sarah Baker. Thanks for putting on this event. I feel so fortunate to work with all three of these wonderful people on stage. So I went in. I'm a chemist by training. I went into science because I wanted to do something about climate change. So I've been in this area for quite a long time. And I have a couple of roles as well. I lead a group of material scientists and chemical engineers. And our group works on everything from trying to come up with those early stage inventions, that basic science we need to transform, to create entirely new technologies, all the way to doing analysis to help companies that exist today figure out how much is it going to cost for me to put on this carbon capture system, or where should I locate my next plant? So our group and our team is really trying to do a lot in this space. And another role that I have is as a PI of projects. And in that role, we work with a lot of different kinds of companies. So I want people to know that we are a resource. We've worked with natural gas utility. We've worked with startups. We've worked with major oil and gas companies looking to decarbonize. And throughout all this thread is this idea that for all of these challenges, we need materials. And we need chemical engineers, and I think we saw that show up on the jobs plot earlier. So thank you.
Thank you, Sarah. Eric?
Is it on? Yep, great. I noticed I sat in the wrong seat. Sorry, Sarah. Eric Duoss, I direct a center at Lawrence Livermore focused on advanced materials and manufacturing technologies. Been at the lab for approximately 15 years and came to the lab with a background in material science and engineering. Long history, in fact, in 3D printing. And you might say, okay, what the heck does 3D printing have to do with climate and energy? But turns out a lot, we think, and I'll speak to that a little bit later. Very passionate about climate and energy, particularly working where I do, think about impacts for national security, which I think are going to be enormous, and had the pleasure of working with Tracie and Brandon and Sarah, and would love to tell you about some of the technology development that we've worked on together, really with a focus on getting these technologies out of the research laboratory and making sure they're fielded, deployed, and have real-world impact. Our director has this saying, focusing on translating innovation to transformation or impact. That's very important to us. And we think there's a lot of workforce needs in this area. We've experienced some of them firsthand, and of course they transcend what we do at a national lab, and I hope we'll start to engage and offer opportunities to partner with the local communities, including the Tri-Valley.
Thank you, Eric. Okay, so a lot of you gave us a good introduction into a lot of the different research areas in climate tech at L&L. Hydrogen, electrification, some 3D printing and materials applications, as well as carbon capture. Can any of you talk a little bit specifically about some capabilities at the lab in climate tech that get good utilization and where you guys have had good experiences with?
Well, I think Eric and Sarah will probably cover the advanced manufacturing side of this, but maybe I can talk a little bit about the computing. I mentioned that's my technical background. I've led a number of projects in that area, and how do you apply high performance computing and simulation to problems of climate. And I think this is something that the lab has a very long history in, and we do very advanced simulations of reactive systems. It's part of our stockpile, what they call stockpile stewardship mission, actually, which is the reason why we have such large computers, but we use those computers for all sorts of things now. So I think it's a very exciting time in computing. We're sort of at this crossroads where we can do pretty sophisticated simulations under pretty sophisticated conditions. Artificial intelligence, machine learning has played a big role in this. And so we've been deploying this both to looking at materials simulations in all of those areas that I mentioned and the areas that Eric and Sarah work in as well, to try to design new materials, right? Can we simulate a material and a change to a material that is either very expensive to do experimentally or in some cases with sort of godlike control, right? We can go in and do very, very surgical changes to materials in the computer that is difficult to realize in reality, but kind of gives us a direction that we need to go. We've also increasingly been using a lot of those techniques to look at a kind of more systems integration level, right? How do we understand what happens? For instance, if we have a chemical reaction that's happening, how does that chemical reaction then manifest across scales all the way to a system demonstration? And I think that historically a lot of researchers have really focused, and this is the natural sort of way academia is set up. We have been focused on one of those scales, right? So you have people who understand the chemistry really well. You have people who understand the engineering of the systems very well. You have people kind of in between that maybe look at reactor scale. What we try to do a lot of is integrating all those together. So how does one scale impact another? An example, we have an initiative that we started a couple years ago. It's called Systems to Atoms, and the idea is to look at all those linkages, and also think about it from sort of the top down. If we understand the environment, the operating environment in which these devices are going to behave, that actually changes the way we understand the materials research. So it's particularly important when we start to look at technologies that are connected to renewable electricity, because there's natural variability. There's variability that's over time, there's variability over space, the resources are different, the feedstocks are different. And so when you think about developing materials for technology, you have to take that into consideration. And at the same time going up the scales, and so looking at trade-offs between things like performance and durability. Maybe you choose one material that has better lifetime but poorer performance. How does that manifest? What's the right choice to make for the technology as you expect it to be deployed? And there's no one answer to that, right? So we develop a lot of computing capabilities to look at those translations across those scales, those trade-offs, and do optimization.
Thanks, Brandon. That was an excellent answer. I think computing is going to be really important to solving complex problems in the future, and climate tech is a huge complex, or climate change is a huge complex problem. I don't know, Sarah, Eric, did you have anything to add to that?
Sure. So I wanted to highlight our capabilities in materials for the transition we need for the climate, as well as analysis. So some people at the lab say that we're a materials science lab. I don't know if everyone would agree. I mean, we're also an engineering lab. We do a lot of things. So the capabilities, some of the relevant capabilities in materials science that we have, at least in the work that I do, pertain to electrification. So specifically, how do we electrify chemical transformations? How do we make the products we need without petroleum? And to reduce emissions, we go from using heat to using electricity to drive these chemical transformations. So this is it sounds kind of wonky and maybe specific, but we can consider electrifying a whole host of processes driven by new materials that we develop and discover. So one of the things we're doing is converting carbon dioxide to ethylene so that we don't have to use petroleum to produce plastic. Another example is we're using new catalysts that we discover and develop to take nitrogen from the air to produce ammonia for fertilizer. We can use electricity to drive water purification and waste remediation. So that's one big area of materials capabilities that we have, and a whole host of characterization tools and synthesis tools that are probably of interest to small companies starting out who could use those resources. And then on the analysis side, I do talk to a lot of companies. And one thing that we find that companies would like assistance with is to understand the economics of the transition. So our chemical engineers with the understanding of the technologies and what's needed, they can help companies understand the options available to them. From our local wastewater treatment plant, how do I decarbonize? How do I extinguish the flare that's there on, I think it's airway, all the way to like where do I site my biomass facility in Northern California? So just trying to highlight some capabilities we have and also ways that we can work with companies.
Great. Hard to follow that, but Sarah mentioned some of the technologies we've worked on together, including electrochemical conversion of CO2 to valuable feedstocks, such as ethylene. I'll just give an anecdotal story there. We created what at the time was the world's best performing reactor to convert CO2 to ethanol, and that was really terrific. Achieved that via partnership, collaboration, working with folks like Professor Tom Jaramillo at Stanford and so forth, and talking with companies and understanding some of the technologies that they were working on at the time. So yeah, really collaborative effort, but we did that at 1 square centimeter. And the way we achieved that was by control over the local reaction environment. And that's where the 3D printing part comes in. It's a three-dimensional sort of reactor volume, and we could have exquisite control, albeit at small scale. And then what happens when you start to go to larger scale? Well, there's different sort of what we call emergent scaling phenomena that take hold, and you really have to understand those and try to address those early. And how do you do that? Well, you do that through a number of scientific engineering methods, including using computation. You can sort of explore the three-dimensional space at different scales, both time and length scales. And you can do that with, I think, some of the things that Sarah was alluding to, some advanced characterization methods, such as in situ sensing. And so what we're trying to do in this space is say, okay, the academic paper that we published and received some notoriety for is good, but how do you take that to the next step, and how do we get people thinking about the so-called science of scale up? And once you get people thinking about that, what is sort of the multidisciplinary workforce that you need to achieve it, and what is, I think there was some discussion earlier about infrastructure, what are the facilities and equipment that's necessary to support that. So that's one of the things we're trying to do at Lawrence Livermore, create this sort of ecosystem that really welcomes the partnership both with academia, industry, and perhaps other entities as well.
Thank you, Eric. Okay, so exploring different partnerships, exploring technology on multiple different length scales, materials development, computing that Brandon mentioned, as well as economic development and siting and planning are things and capabilities that L&L is involved with in this space. So I want to ask you one more question, and then I think we'll have time to go to the audience for questions. So what have you observed at L&L as the biggest barriers towards employing a future workforce in green energy? Any of you guys could answer that question.
I could jump in. Eric mentioned the science of scale up. That's an area we're trying to grow at Livermore. I think it's safest if I speak from my personal experience there. In my academic training before I came to Lawrence Livermore, I had absolutely no idea how to. I knew how to do hypothesis-driven science, but I had no idea how to think about getting what I was doing in the lab to actually matter. And I think that might be I've seen it play out time and time again, where we prove something works, we have that eureka moment, and then we work on the wrong thing to develop that technology for many years. So that is one area where we're trying to improve our competency and improve that scale-up mindset to help the people who work at the lab realize the impact of what we do, but also we're trying to bring that in through like some of the work that Tracie's doing when we bring in students and interns, and just really try to get people to think about how the technology has to perform in the real world, and how that influences what you do at the bench. That's it.
Thanks, Sarah. Did you want to add, Brandon?
Maybe, I mean, it's sort of echoing the same idea, but I think that the national labs, at least the way I view it, they're sort of a bridge between, academic and industry environments. In other words, between, basic research and market deployment. And so that's a very large gap if you think about it. And I think we've been trying to navigate that internally through some of our initiatives, and all of us have had a similar, I'd say, professional journey in coming to the realization of how important that is. But that's something that's not taught, really. And so, we hire mostly highly educated postgraduate, not exclusively, but at least in the areas that I work in. And they come with a very narrow, I would say almost capability-driven focus, where, they do one thing well. They're looking at how to apply that one thing to the problem space that they see. And I think, transforming that mindset into something that's really problem-focused. What are the right problems to look at? Do these problems matter? The solutions need to match the problem. And that's a paradigm shift, I think, for a lot of people with technical training like what I have. And it's something that really comes only on the job right now, but we could probably do a better job of anticipating that, I would say.
Okay, that's great. Okay, so having more of a skill-up mindset and kind of figuring out how to design for manufacturing and design for scale and things like that. Okay, so yes, we have time for questions now. Are there any questions from the audience?
Great. Thank you. Scientists connecting the dots at almost like at a micro level. And my question also connecting back to even the previous panel, because if we look at the climate problem, right, clearly that's where, we're thinking about either the new material, clean energy, and then because my startup is actually doing food tech, we help the food operator to actually reduce the overproduction by doing accurate forecast. Now, we know that not only basically improve their bottom line, but that helps with the whole green gas and the landfill problem. So what I wonder is, what is needed, right, from you guys' point of view, and also from a larger scheme, where how do we, from investment and from like solving problem, step back and connecting the dots to see, okay, all these different new material and carbon removal, and then food waste reduction, how these different means fit in a bigger, right, objective as we try to solve the climate challenge. I just want to hear the panel's perspective on this.
I think it's been said, but it bears repeating. Carbon removal is important, but decarbonization is absolutely the most important thing we can be doing today, and part of that is increasing efficiency. I mean, it sounds like what you're doing is really important. If I understand your question, if we're doing anything related to food waste, not that I know of, but maybe on the end of life of food, for sure, that is a major challenge. And so, thinking about how to reduce landfill emissions, my group creates materials that can do gas separations to utilize biogas from landfills. So definitely interested to hear more from you about if there's a way that we can help.
So by background, I worked 31 years before retiring from Lawrence Livermore, worked 10 years in the private sector and in academia both. And I've had contracts going both directions, and I've been a retired contractee at Lawrence Livermore for the last 5 years. I was actively involved in technology transfer, and one of the things I didn't hear you talk about was CRADAs. Back decades ago, CRADAs took 6 months, possibly a year, And it gets back to the regulatory thing that if in fact the regulatory environment is too onerous, people just say, screw it, I'm not going to bother, regardless of how good your stuff is.
Well, create a cooperative research and development agreement. That's a legal sort of vehicle, partnership vehicle to work with, for example, ourselves as a national laboratory and other entities within the federal government. Great point. And and what I'll say is we've recognized that for some time. We have a new facility called the Advanced Manufacturing Laboratory. The charge of that facility is to partner with the external community. It sits in our Livermore Valley Open Campus. It's really easy to access, in some cases perhaps too easy. We just had a visitor who was testing us for First Amendment audit purposes, if you ever heard that. That was fun. But within the Advanced Manufacturing Laboratory, we've worked with what's called our Innovations and Partnerships Office. Maybe there's some representatives here today. They handle the technology transfer aspects, the cooperative research and development agreements, and they developed something called, they call a master CRADA. Now, the details matter, but we found if our partners are willing to agree to this master CRADA, it can happen in a matter of weeks now. So that's been a great accelerant for us. However, if lawyers get involved and start looking at the intellectual property terms and start to negotiate those, then kind of all bets are off. Another thing that we found is increasingly we're undergoing things like foreign partner review, and those can take quite a long time. We recognize this as a problem, and we're trying to make sure that the folks that oversee our efforts at Department of Energy and so on understand it, and they're certainly doing what they can do to try to address it. Yeah.
Okay, thank you, Eric. That actually, I was going to say that, okay, so this should be our last question because we have to wrap up after this. Okay.
This is for Sarah. It's a two-part question. When you compare the cost of ethylene from petroleum and the cost of generating it with electricity from carbon dioxide, how close are you to competitive? And the second part is, does it require a continuous process, or can you track the ups and downs of solar and wind?
Yes. So this is why we do techno-economic analysis early on, to understand those biggest levers that will drive down the cost of our new transformational disruptive technology. We are not near cost parity for CO2 converting to ethylene when we compare to petrochemical ethylene. Maybe threefold higher, something like that. But the bigger challenges that we face have to do with durability of the new materials that we're putting in these systems. And so that's part of the science we do, right? We take that techno-economic analysis, those insights, and I'm probably talking too long because we're trying to wrap up, but now we take it back down to like, okay, now we need to do basic science on durability of materials. So we're not there yet, but we understand what we need to do, what we need to improve on to get there. And yes, electricity cost is the biggest driver for electrified chemical production. And so yes, developing a technology that can follow those ups and downs would be really helpful, and something we're working on.
Okay, thank you, panel. Thank you, Sarah, Eric, and Brandon. Let's give them a round of applause.